Hi there, my name is Jackie Decker, and I'm going to introduce you to how you might use integer tiles and algebra tiles to do integer operations and simplify polynomial expressions. In my experience, if we reactivate student understanding of base 10 materials, that's going to go a long way. So if we can remind students that they get their name from either their area or their volume, that's why a 1 by 1 is often defined as 1, a 1 by 10 is defined as 10, and a 10 by 10 is defined as 100. Thinking about that, when we now bring out algebra tiles, we see that we have a 1 by 1, which also has the name of 1. But if we picture the long rod as maybe made of something flexible, so it can stretch and it can shrink, and it can actually represent anything. And when we don't know what something is represented by in math, we call it X. So this is the X tile. And if we use these red tiles as positives, we can just flip them over and call the opposite side negative. We're going to ask our students to represent each one of these numbers one at a time. We're going to give students lots of wait time, and then we're going to watch what students do, notice and name what they're doing, share different student strategies with the class, and we're going to build their understanding of number, of negative number, of addition and subtraction, step by step. When we ask students to represent 5, most of them will pull out 1, 2, 3, 4, 5 positive integer tiles. When we ask them if there's another way, give a little bit of wait time, some students might do this. And when asked to explain why that's still 5, they'll tell us that a positive 1 and a negative 1, they might say cancel out, they might say add up to 0. If we say this is actually a 0 pair, we're going to be able to use the 0 principle for harder problems. Similarly, when we ask students to represent negative 2, they'll take with negative 1, negative 2, and they might add some 0 pairs and let us know it doesn't matter how many 0 pairs we add, that is still representing negative 2. When we ask students to represent 3x, a common misconception we see is students showing us 3 and an x. However, this is 3 plus x. And a quick conversation with students asking them, well, what's this? And they'll say x. We'll say how many? And they'll say 1. If we say, well, how would I have 3 of those or 3 x's? They'll say, oh, and they will change their thinking and they will demonstrate this as 3x. When we ask students to solve 5 minus 3 or 5 subtract 3, some students will choose 5 positive tiles and they'll think about subtraction as removal. Take away 1, take away 2, take away 3, we're left with 2. Some students will leave those 5 there and think about this as 5 plus negative 3. And so they'll bring over 3 negative tiles and they'll say, this is a 0 pair, this is a 0 pair, this is a 0 pair. So again, we're left with 2. When students solve negative 5 plus 3, they'll count out negative 1, 2, 3, 4, 5, and they'll add plus 1, plus 2, plus 3. So we have an addition of 3. Oh, there's a 0 pair, there's a 0 pair. There's a 0 pair, and we are left with negative 2. When we ask students to represent 4x plus 1, they'll bring out 1x, 2x's, 3x's, 4x's, and a positive 1. If we ask them then to add that to 2x, or negative 2x plus 2, they will bring out their negative 2x plus 2. Students will automatically, most of the time, rearrange this so that they're putting all the x's together and all the 1's together. And if we tell them you're collecting like terms, we're noticing and naming the math. They will often recognize that the 0 pair or the 0 principle now applies to x's as well. So there's a 0 pair, here's another 0 pair, and our simplified expression now is 2x plus 3. Once students have built some skills step by step, we can open up these problems. This is an example of a more open problem using algebra tiles. How many different expressions can you model using exactly 5 algebra tiles?